Sandra?
Yes.
Yeah, okay. So it is my great pleasure to announce a talk by Sandra Cerrai from Maryland University. Sandra has been working for many years on stochastic partial differential equations, on the existence and uniqueness of solutions to stochastic reaction diffusion equations, and also on regularity of solutions. And later he moved to asymptotic theory, to large deviations problems for stochastic PDEs, also for Cramer's approximation for stochastic wave equations. And also she worked, and she's still working on Schauder estimates for infinite dimensional PDEs. And today the talk is again about asymptotic analysis of stochastic PDEs. So thanks, please start, Sandra.
Thank you, Ben. Thank you for inviting me. It's a great pleasure to see you again and to give this talk in this unusual time for me. So you see, it's a seminar in 2 different days. So this is a rarity. For me, it's the 21st. For you, it's the 22nd. So, and okay, so what I'm discussing in this talk. So in this talk, I am considering some particles that are moving together with an incompressible flow in the plane, and the stream function is denoted by H. So if U denotes the density of these particles at time t and in the position x, then U is described by this partial differential equation. Okay, so this is the equation, and this will be equation 1. But now what I do is to consider the same equation, but with some perturbations. So what I assume is that this flow has a small viscosity that is described by this term here. And then you see the particles are taking part in a slow reaction. And this slow reaction has 2 components, a deterministic part and a stochastic part. And here you see this epsilon, this parameter epsilon is a small parameter, and it's included in this equation in such a way that all the perturbations have the same strength. Okay, so this is the right scaling that I have to consider in such a way that all these perturbations have the same strength. So what is my problem? If you consider a fixed time interval 0 capital T, then it's not difficult to prove that the solution of the perturb equation, which is denoted by U hat epsilon, converges to the solution of the unperturbed equation in probability. Okay, but this is true only on a finite time interval. Okay, so you fix 0 capital T, you consider the 2 systems in that fixed time interval, and what you have is that this limit is satisfied. And somehow this is easy to prove, and there is nothing very, this is the trivial limit, okay, on a finite time interval. But of course, you see, more interesting things are happening if you allow to wait longer. Okay, so on a time frame that is not anymore fixed, but is growing with epsilon, with the order 1 over epsilon. So in that longer time frame, what you will see is some non-trivial limit. Okay, and so what we will show somehow is that U hat epsilon minus U, this difference as order 1 as epsilon goes to 0. On this longer time interval. And my talk is about this, about trying to understand what do we get, what is the non-trivial limit that we get when we allow to wait longer, okay? And we wait on a time interval of order 1 over epsilon. To describe this long time behavior, it's useful somehow to do a time change. So we define u epsilon tx as u hat epsilon at time t over epsilon. So we do this time change. And with this time change, the new variable u epsilon satisfies now this equation here. And so now you see that the perturbation have order 1, while we have this part here. This is fast changing and has order 1 over epsilon, okay? Of course, for some other homogeneous linear process W, okay? So from now on, what I will do this time change. And so instead of working on a time interval 0 t over epsilon, I will work now again on a time interval 0 capital T, okay? So what is our goal? Our goal is to understand the limiting behavior of the solution u epsilon tx of equation 3 as epsilon goes to 0 in a fixed time interval. And in particular, what we will want to do is to describe the limit of u epsilon. And in order to do that, we will need to consider some SPDEs that are not defined in a non-standard setting. You see, our SPDE, the SPDE whose solution is u epsilon, is an SPDE defined on the plane, but at the limit we will have to introduce a new SPDE on a non-standard setting, and this non-standard setting is a setting where the space variable change on a graph, which I will call gamma, which will be obtained by identifying all the points which belongs to each connected component of the level set of the Hamiltonian. I will give you all the details about this, but you see, this just to tell you what is my goal. My goal is to prove that u epsilon converges to the solution of an SPDE that is now defined on a graph, and this graph is naturally associated to the Hamiltonian that I have, to H, okay? Let me give you, first of all, the assumption that I'm making on the Hamiltonian, on the noise, on the coefficients. So concerning the string function h, what we assume is that h is smooth. Here I wrote C infinity. In fact, I mean, it's enough to have C4. And this has bounded second derivatives. Then the second assumption is that this h has only a finite number of critical points, x1 up to xn, and the matrices of the second derivative at these critical points are all non-degenerates. And also the value of h at the different critical points is always different, okay? And then last condition is a condition on the growth of h, of the gradient of h, and on the Laplacian of h for x large. So what we assume is that for some, if x is, there exists some constant c such that if x is greater enough, then what I have is that these conditions are satisfied, okay? So at infinity, the growth of my h is super quadratic, and then I have this condition, okay? So for convenience, what we assume is that the minimum of h is equal to 0, but of course, this is only for my convenience. There is, this is not really an assumption. What about the noise? The noise that I am considering is a spatially homogeneous linear process, and associated to this spatially homogeneous linear process, there is a spectral measure, which I will call mu. So what does this mean? What is the meaning of having a spatially homogeneous linear process with spectral measure mu? This means that W is a Gaussian random field defined on some stochastic basis, omega f, with some filtration and some probability. And what I assume is that you see the mapping that associates 2x WTX is continuous with respect to t and measurable in both variables pure more surely. The second condition is that if I fix x Then the process WTX with X fixed is a one-dimensional Wiener process. And also, if I look at the covariance for T and X fixed, what I find is this. So what I find is that the covariance between WTX and WSY is given by this expression here. And this lambda here is the Fourier transform of this measure mu, which is called the spectral measure of my homogeneous Wiener process. Okay. What is possible to prove is that with this definition of spatially homogeneous Wiener process, WTX can be written as this series. And this series is given in terms of this beta j, which is a sequence of independent Brownian motions. And in terms of these objects here, that are nothing else than, you see, a basis for the reproducing kernel of the noise. I understand if you are not familiar with this concept, this is not very important. I mean, this is fundamental, of course, but it's not important in order to follow what I am going to say later on. This is what it is. I mean, one can write WTX as this formal sum. And here what we have is that Uj is a normal basis in L2 of R2 with values corresponding to the measure mu. And here you see there is this S here, which means that U of minus X, if you consider the complex version, this is equal of U of X. Okay, and M, oh wow, this is not M, here there is a mistake, this is mu, sorry, this is mu, the spectral measure. Okay, so this is what we have for the noise. And what I will assume during my talk is that the spectral measure mu admits a density. A density which I will call M. And what I will assume on this M is that it belongs to some LP of R2. And here P, here should, there is another mistake here, P is considered greater or equal than 1. And in my analysis, I will distinguish the case P is equal 1 and the case P bigger than 1. Why this is important? Because in the case P equal 1, what I have is that mu, I mean, M is in L1, and so mu is a finite measure. And this means that the noise is smoother and actually lives in a space of functions. As soon as P is bigger than 1, this is not anymore true, and so things become more complicated. So the case P equal 1, which means finite spectral measure, it's simpler in the analysis. The case P bigger than 1 means that the noise is not living in the space of functions, and so the analysis is more complicated. And in my talk, I will make sure to distinguish the two cases. How about the coefficients? The coefficients are nice. So in this work, we didn't want to have any problems coming from the coefficients. So we assume that both of them are Lipschitz continuous. So this means that you see, if you take a weight rho in L1 and you take U that is L2 in R2 with respect to this weighted measure, and if V is in the reproducing kernel of the noise, let's take this, I mean, it's too complicated to say what is the reproducing kernel, but you see, if V is in the reproducing kernel, what one has is that one can define these coefficients here that now you see are, if you want, the abstract coefficients that you can construct in terms of B and G. Okay, so we define this. And what we have is that, first of all, B is an operator that maps L2 into L2 and is Lipschitz continuous. And the G is an operator that maps L2 into Hilbert-Schmidt operators defined on the reproducing kernel with values in the space L2. And this operator turns out to be Lipschitz continuous. But notice that this is only true when P is equal 1. Because when P is bigger than 1, then you lose the fact that this operator G is taking values in the space of Hilbert-Schmidt operators. And so, as I was saying, the analysis is more complicated. But we will go back to that. Okay? Okay. So, with this assumption and under suitable other condition on the weight, what is possible to prove is that if you fix your time interval 0 capital T, for every Q greater or equal than 1, the stochastic PDE defined on the plane, the equation 3, admits a unique mild solution, which I will call U epsilon, which belongs to LQ omega with values in the space of continuous trajectories with values in L2. Okay, so this is where I can find a solution. And what does this mean? In which sense I say that these are solutions? These are mild solutions. This means that U epsilon satisfies this equation that is written in this integral form. And here S epsilon is nothing else than the semigroup that is associated with this linear differential operator. Okay? So I have here there is a mistake. This is not L epsilon hat, but this is L epsilon. So I have this linear operator. I can associate to this linear operator a semigroup S epsilon, and the mild solution is a process U epsilon that satisfies this integral equation. Okay. In order to study, so I have this object here, I have this equation, okay, and I want to study the limiting behavior of the solution of this equation. As you can imagine, it's fundamental, first of all, to understand what is the limiting behavior of the linear part. So what is the limiting behavior of the semigroup S epsilon? So in order to do this, I first consider the linear deterministic problem given by the operator L epsilon. Okay, and here I recall you that L epsilon is this second order differential operator. So what can I say about this linear deterministic problem? What I can say, as I was saying before, is that the solution V epsilon Tx can be written in terms of the semigroup S epsilon, which is associated to the operator L epsilon. And so more precisely, what we have is that we can write, you see, V epsilon of Tx as S epsilon phi x, which is nothing else than the expectation of phi of X epsilon S. And X epsilon T, sorry. And X epsilon is the solution of this stochastic differential equation. And here W is some two-dimensional Brownian motion that is defined on some other stochastic basis. This has nothing to do with the stochastic basis where I define my homogeneous, spatially homogeneous linear process, okay? So this is another noise defined on another probability space, which defines this X epsilon, this process X epsilon, that is associated to the operator L epsilon and to the semigroup S epsilon. Okay. So now, when we want to study the limiting behavior of the solution of the SPDE, we want to study the limiting behavior, first of all, of the linear deterministic problem. And so, as you can imagine, we want to study what is the limit of S epsilon, of the semigroup S epsilon. In order to do this, and this is somehow a very delicate part, I have to introduce some notation. And I have to tell you, I have to introduce at this point the graph. And I have to say in what sense this graph is related to all my problem. So I have the Hamiltonian H. I fix a value Z, the Hamiltonian as a minimum at 0 and is taking values greater or equal than 0. So for every Z greater or equal than 0, I denote by CZ the level set corresponding to the value Z, the level set of the Hamiltonian that corresponds to the value Z. And you see, this level set may be made of several connected components. And each connected component is denoted by CK of Z. So C of Z is given that by the union of CK of Z for K that goes from 1 to some NZ. Okay? And what you have is that if X is the solution of the Hamiltonian problem, so if X is the solution of this problem here, what you have is that if you start from some point X in R2, the solution remains on the same connected component where you can find X. And so what you have is that CKX H of X, this object here, is nothing else than the connected component of the level set CH of X, which is containing the point X, okay? So once you start from the point X and you consider the unperturbed Hamiltonian, the motion is all within the same connected component of the level set of the Hamiltonian. Now, for every value of the Hamiltonian Z, and for every K that goes from 1 to NZ, remember, K from 1 to NZ is the these are all the connected component of the level set CK. We denote by TK of Z the integral over the connected component CKZ of 1 over modulus of nabla H, integrated with respect to this LZK, and LZK is the length element over the connected component CKZ. And what is possible to prove actually is that this TKZ, and this is well known, you see TKZ is nothing else than the period of the motion along the level set CKZ. And also, and this is very important, if I introduce this measure here, this is a probability measure, because it's normalized by dividing by TKZ. So if I introduce this probability measure, this turns out to be the invariant measure of the Hamiltonian system on the level set CK of Z. Okay. Okay. So now, how do I introduce the graph? So what I do is the following. I so what I do, I have my points on the plane. So I want somehow to map every point on the plane on a graph. And how do I do this? I identify all points in the plane that belong to the same connected component of a given level set of the Hamiltonian. So all points on the same connected component of a level set of the Hamiltonian are all identified in a point, and this is a point on a graph. And so this means that what I get is a graph which is made by several intervals and the vertices, which I will call O1 up to OM. And these vertices, of course, are of two different natures, because vertices may correspond to critical points. I mean, they may correspond to local extrema of the Hamiltonian, and in this sense, and in this case, I have extremal external vertices, or they may correspond to saddle points, and in that case, I have internal vertices. So just to make you understand what I'm talking about, this is the situation, okay? So here I am on R2, okay? So here I have a R2, and you see this is my Hamiltonian H, okay? And this corresponds to this local minima, this corresponds to this local minima, okay? And this corresponds to this saddle point, which I have here. And what I do, for example, if I fix, I don't know, a point here, this corresponds to this level set, and all the points that are on this level set are mapped into this unique point. Of course, if you are here, you see, if you are here, you have two connected components, and so they correspond to these two different points. Okay, so this is what I do. So this is how I construct my graph. Okay, by identifying all the points on the same connected component of a given level set of the Hamiltonian. So this defines somehow a map. This is my graph gamma. So this somehow defines a mapping from the plane into gamma. And this is what I do when I introduce the identification map. The identification map is the map that associates to every point R2 the corresponding point on the graph. Now, if you have a Hamiltonian which has only one minimum, so an Hamiltonian like this, then the graph somehow is trivial, is this one, and so you see H is a global coordinate for your graph. But in the case you have, you see several critical points and saddle points, then H is not anymore a global coordinate. And so somehow it has to be integrated with another component, with another coordinate. And this is what we have. So what we have is that we can write now the identification map, pi of x, with two coordinates, h of x and k of x. H of x denotes the value of the Hamiltonian at the point x. And k of x is telling you on which connected component of the level set corresponding to the value h of x you are, okay? And what you have is that both k of x and h of x are first integrals for the Hamiltonian. And of course, k is a discrete one, h is a continuous, but they are both first integrals of the Hamiltonian system. So, Friedel and Wenzel in 2002 studied the limiting behavior of this process here, of the process pi epsilon equal pi of x epsilon t. So x epsilon is the perturbed Hamiltonian. You project this motion that is that motion on the project this motion on the graph, and this is now a process which is not a Markov process but is a process that lives on the graph, and their point was seen if they could identify a limit for this process. Okay, and so what they studied was the limiting behavior of this process in the space of continuous path with values in the graph gamma. And what they proved was the following. What they proved that the process pi epsilon, which describes what? Pi epsilon is a pi of x epsilon. So the motion of x epsilon has somehow two components. You have a fast component on the level sets of the Hamiltonian, but now because of the presence of the noise, and I mean because of the presence of your perturbations, so what you have is that you have some transversal motion, okay? So you are leaving the level sets, and so, but this motion so the motion on the level set is much faster than the motion of h than the change of the value of the Hamiltonian, okay? And what they studied, and so pi epsilon is describing the slow component of the motion of x epsilon. And what they prove is that this converges in weak, in the sense of weak convergence to some diffusion process y bar that is now a diffusion process defined on the graph gamma. So let me, and you see, and this is what you see, what it means in a more rigorous way. This means that if you take an arbitrary continuous operator defined on the space of continuous trajectories with values in R, what you have is that this limit is satisfied. This is just the notion of weak convergence in the space C0T with values in gamma. So this is the result by Friedel and Wenzel in 2002. What can we say about this? Let me tell you what happens in the simple case when H has only one critical point. And then from that case, you see what you can expect in the general case. So if you apply the Ito formula, what you get is that H of X epsilon is given by this. So you see that H is the slow motion because it's a motion of order 1, while you see, if you look at X epsilon, there is the term 1 over epsilon in front of the skew gradient of the Hamiltonian, okay, which describes the fast motion on the level set of the Hamiltonian. But if you look at H of X epsilon, this is of order 1. And what we have is that since X epsilon rotates many times along the trajectory of H before leaving, before H of X epsilon changes in a sensible way, what you expect is that this is, you see, the system has enough time to produce, to be subject to some averaging, okay? And so what you expect is that for epsilon small, this quantity here can be approximated by this quantity here, where B is defined by this. So what is this? B of C is nothing else than the average of this function here, Laplacian of H, with respect to the invariant measure that you have on the level set, on the connected component of the level set. Okay, so this is what you have. Because you have this many rotation before H of X epsilon changes a little bit, and so you have time to have averaging. And the averaging, of course, is with respect to the invariant measure of the Hamiltonian on the level sets. In the same way, if you look at this is also something that you can approximate by this, where again, A of C is obtained by averaging this with respect to the invariant measure, okay? So this is what we have. And now remember, you see, let me go here. This is what we yes, this is what we have. This is the equation satisfied by H of X epsilon. So you have this the deterministic part, you have this stochastic part, but for both parts you have averaging. And so what we have is that you see the process H of X epsilon can be approximated through a process which is associated to this operator, to this differential operator, where now you see this coefficient AZ and BZ are obtained by averaging with respect to the invariant measure, okay? So what do we have in the case? We don't have one minimum only, but we have several critical points. Okay, so in this case, the situation is more delicate. And so what they proved is that the generator L bar associated to the limiting process Y bar that lives on the graph is given by several differential operators L bar K, which are defined on each edge. And they are given by the same expression, but now they depend on K because you see on each, and so they depend on K because they depend on the level sets where you are and on the connected components. So they depend on K. But they are defined exactly in the same way as I told you before. And now you see the domain is defined as a set of continuous functions on the whole graph, which are twice continuous differentiable on the interior of each edge. And then they satisfy some gluing conditions at the vertices, which you see are given in terms of TK, and you see integrals with respect to the invariant measures. But you see, I don't want to go into this because otherwise I never finish, okay? Of course, this operator L bar is a non-standard operator because it's a differential operator on a graph endowed with this gluing condition, and also it has degeneracies at the endpoints, so it's a completely non-standard operator. But nonetheless, Friedel and Wenzel proved that this operator is the generator now of a Markov process on the graph. And so they could introduce this transition semigroup S bar T, which is associated to the Markov process Y bar, and which is, of course, defined as usual as you see the expectation of F computed in the process Y bar. Okay. You have this process Y bar, and so you can introduce the transition semigroup, which now acts on functions defined on a graph. So now let me go back to the linear problem. So we have this linear problem. The solution is given in terms of the semigroup as epsilon. And now you see I have the Friedling-Wenzel result. What I have is that the limit as epsilon goes to 0 of expectation of f pi x epsilon for every f that is continuous, that is a continuous operator defined on the space of continuous trajectories with values in the graph. So what we have is that this limit is given by this expression here. I think that now I have some problems with my connection because, so I'm sorry, I have to do something. Sorry. Okay. Okay, so what I would like to use is this Friedling-Wenzel result. But unfortunately, things are definitely more complicated. So I cannot use this in order to get the limiting result for the linear problem and then for the stochastic PDEs. This is not possible. And so there is much more work that has to be done. And in order to do that, somehow I have to define, you see, a way to go from functions defined on the plane to functions defined on the graph, and I have to, yes, I have to do some work. So the first thing that I do is the following. If I have a function u that is defined on the plane, I define this new function, which is now the projection of the function from the plane to a function on a graph. So I don't know how to call this, this symbol, the LaTeX symbol is wedge. So let me call this wedge. I don't know what is the name for this symbol, but U wedge now is a function defined on the graph and is obtained by taking the average of U on the connected component corresponding to K and Z. And here, this mu zk, I recall you, is the invariant measure of the Hamiltonian on the connected component. In the same way, oh wow, again. I don't know what's going on with my Wi-Fi connection.
No, we can hear you.
Yes, you can hear me, but the problem is that you cannot see my iPad moving. Changing pages because my iPad is getting frozen. Yeah. Okay. If this is repeating, then probably I go to the computer. So, okay. So, and the next thing that you can do is that if you have a function that is defined on the graph, you can extend this function, or you see, you can bring this function to a function defined on the plane, and you define f v as f composed with the identification map pi. And what you have here is that while f is the same as fv wedge, it's not true that u is a u wedge v. Okay, so if you do this operation twice, you do not go back to u, and this is a major problem in all what we are going to do. Next, I introduce weights in R2 and gamma, because you know that when you are dealing with these SPDs on the plane or in this unbounded graph, you need to introduce some weights. But here the choice of weights is very delicate, and somehow you have to choose weights that are compatible in this way of identifying points on the plane with points on the graph. So you have to choose accordingly the weights that you want to use. And so the first things that we had to assume was that there exists some continuous mapping gamma which satisfy this property here, okay? So this sum is finite. And in particular, what we could prove is that if now you take gamma v, so if you bring back, this gamma is a function defined on the graph, and if you bring back this function on R2 and you introduce gamma v, then this function is L1 in R2, so it's a good weight for your analysis. And now that we have gamma and gamma v, we introduce the space H gamma, which is the weighted L2 space with respect to this measure gamma v dx. And we define H bar gamma, which is the L2 space on the graph with respect to this measure, which is nothing else, if you want, than the projection of this measure here on the graph. Okay? And this new gamma is a finite measure because of the assumption that we made on gamma, so everything is fine, okay? So now, if we look at the semigroup S epsilon on this weighted space, H gamma, we assume that this semigroup is well defined on H gamma, and this property is satisfied. Of course, we had to find examples when this is true. And in fact, we could prove that there exists a strictly positive continuous function gamma defined on the graph, which satisfies this property here. So such that S epsilon is well defined as a bounded linear operator on the space H gamma, and also this fundamental property is satisfied. Okay, but this required some work, but we could prove that there exists such a function gamma. Once we have this, so we have the right space where we want to study the convergence of the semigroup S epsilon, and together with Mark Friedlin, we proved that you see this property here is satisfied. So what we have is that you see the semigroup S epsilon converges to the semigroup S bar. So we proved this result here. And this result is uniform with respect to t on an interval tau t, capital T. We cannot go with a uniform limit up to 0 because at 0 there is a boundary layer because of the fact that this UV wedge is not the same as U. I mean, there are problems, okay? But you see, on an interval that is away from 0, we could prove this uniform limit. And this is a limit that is for x fixed, but what we proved is that in fact, and you see, and in fact what this means is exactly that we have the convergence of the semigroup. And in fact, what is possible to prove is that this limit is also true in H gamma and in H bar gamma. Okay, so they are also true in those spaces. And here you see the fundamental assumption that we had to make was that the period is not constant. So we had to assume that at each z, more than that, we had to assume that for every point on the graph, the derivative of the period was different from 0. This is a technical assumption, but it's a fundamental one. So this, for example, rules out the case of a quadratic Hamiltonian. This said, you see how to prove this limit. One say, okay, we use the Friedlin-Wenzel theorem. So we have this limit here. But in fact, this limit on its own is not enough, and a lot more work has to be done in order to prove the limit. And in fact, one needs to prove these two limits. One needs to prove that this limit is satisfied and this other limit is satisfied. Okay, I mean, this is all these, the proof of all these limits is extremely technical, is very delicate, and is based on averaging on the interior of the edges of the graph, and on a very refined analysis of the exit times of your process x epsilon from the critical points, which corresponds to the internal vertices of the graph. I think here I wrote a few things about these limits. Again, is frozen. I'm sorry. Yes, I prepared these a few slides, but I think we can skip these slides. But I mean, just to tell you, no, this is not working. So I'm so sorry. I have to do a different thing. I'm sorry, really, but my connection tonight is not working properly. So I'm using my computer now. So let me find here. Moment. Okay. Do you see now my screen?
Yes, now we can see it.
Yes. So this is the only thing I can do. Okay. Now you see the full presentation, and now I have to go where I was. So I skip this limit here, and now you see so we were here. Okay, so what we wanted to prove is that this limit is satisfied, and in particular the limit for the submit group is satisfied, and this is what we proved with Mark. So now let me go back to what we wanted to do. Now we know what happens in the linear case, so let me go back to the SPDE. And for the SPDE, we have this, and what we want is to study the limiting behavior of the solution U epsilon in this space here. And this, I recall you that the spatially homogeneous linear process is given by this expression, and so the solution U epsilon is a mild solution if this is true. And the well-posedness of this problem has been studied, for example, by Peshant and Zapchik in their paper on 97, so everything here is fine. So now I introduce the SPDE on the graph, and the SPDE on the graph now is given by this SPDE here. And here L bar is the generator of the limiting Markov process constructed by Friedin and Benzel, which is a process on the graph. And here W bar is the projection of the spatially homogeneous linear process that is defined on the space R2 on the graph. So what you have is that W bar TZK is, is the projection of the noise, which is defined by this formal sum. Okay, and here what you have is that you have this Fourier transform of UJM, but now you project this function on the graph by taking this operation wedge. Okay. So now I have this SPDE, which is defined on the graph, and the limit result that we proved, so this is the final result that we got, was that if you fix an arbitrary initial condition that is in the space H gamma, any Q and any tau less than T, what we have is that the limit of U epsilon T minus U bar T V, because of course here U epsilon is defined on the plane and U bar is defined on the graph, so you have to make them compatible. So either you take U epsilon and then you subtract U bar wedge, or you take U bar V, or you take U epsilon wedge and you subtract U bar. But in both cases, what you have is that the limit of their difference is equal 0. Okay, and so you can approximate the solution of the SPDE on the plane with the solution of the corresponding SPDE on the graph. So how do we do this? And here, as I was telling you, there is a major difference if we are considering a final spectral measure, or we are considering a spectral measure that has a density that is in LP, but for P bigger than 1. So the spectral measure is not final. And
Sandra,
yes.
to interrupt you, but
yes.
We should probably finish in 5 minutes.
Ah, okay. So if you finish, yes, okay. So I see what I can say, and then I stop because you see already you have seen the result, and so what I was doing now was some description of what one does. So let me see. One moment, because. Okay, I can tell you what happens in the case of a finite spectral measure. So in the case of a finite spectral measure, as for the semigroup S epsilon, it is also possible to prove that the semigroup S bar is well defined on the weighted space defined on the graph, and this estimate is satisfied. And also, since we are dealing with a finite spectral measure, as the spatially homogeneous linear process in the plane is living in L2, the same is true also for the projection of the spatially homogeneous linear process on the graph. So also W bar is taking values in the space of square integrable function. And so you see there is no problem in defining the stochastic convolution for S associated with S bar and the projected noise. And so you see this equation is perfectly well defined in the sense that you don't need any regularization that is coming from S bar in order to give a meaning to this stochastic convolution, because the noise is already smooth enough to make everything, well defined. Okay, so this is a perfectly well defined equation, and also, and this is true because you see we have this property for the multiplication operator G, and so you see this means that we don't need any regularization, and the limit is satisfied you see, I mean, there is work to be done, but somehow is satisfied in a natural way once you have the limit for the semigroup S epsilon to the semigroup S bar. As I wanted to say later, but I think that at this point it's better if I stop, things are much more delicate when you have that the spectral measure is not finite, because in that case the noise is not smooth, the noise is singular, is living in space of distributions, is not living in a space of square integrable functions, and so in this sense you need some smoothing effect of the semigroup S epsilon, which is something that you have. But what you want is that at the limit, you have a regularizing effect of the semigroup S bar, which is this semigroup that you define as the semigroup associated to the limiting process Y bar. So you see, it was extremely complicated to get any smoothing effect for this S bar, which was just the semigroup associated to this diffusion operator defined on the graph. And so in order to do that, we had to do some analysis of the heat kernels of S epsilon, proving that some uniform bounds are satisfied, uniform with respect to epsilon. And so in this sense, S epsilon inherit some smoothing properties of S epsilon, and we can conclude our result. And we can prove the same limit also in the case of a spectral measure which is not finite. So I stop here, and sorry for, all these disruptions with my connection and for rushing at the end. So somewhere there was a thank you, which is later. So thank you.
Thank you very much for a very interesting talk. Are there any questions? I would have a question about your assumption about the noise. You assume that the Wiener process is space homogeneous. Why is it important? You don't claim that solutions are space homogeneous. Your initial condition is any function.
Yeah, probably. Probably what I did was somehow to put myself in a situation that I knew well, which was the situation considered by Pejat and Zapchik in their paper, and so somehow wanted to be in that framework. But I agree with you that I'm not using any of this property for the solution, so probably I could have considered more general situation. Yeah.
Are there any other questions? Well, if there are no questions, then let me only remind everyone that you have received invitation to a coffee break, so we can meet again in a few minutes. And now, if there are no more questions, then I can close the meeting, unless I am gone. You wrote something to everyone. Would you like to ask the question or comment? Yeah, so Gan, please, I should allow to talk. Yes.
Hi, thank you for your talk. It's very interesting. I know that this is the problem you consider where the operator can create a semigroup, and all of the proof based on the property of the semigroup. So if in case that the operator cannot generate a semigroup,
I'm sorry, it's a bit broken. So can you repeat your question, because it's a bit broken and I don't understand well.
It means that the equation you consider, the operator can generate a semigroup, and all of the proof this result here depends on the property of the semigroup. So if you have a case that the main operator in your equation cannot create a semigroup, so is there any result about the convergence of the solution on the plane connect to the solution on the graph?
So are you asking about the semigroup S epsilon?
Yes. I mean that in case that we cannot generate a semigroup when...
No, the point here is this. So let me go back at the very beginning. So what I have is this. I have a stochastic PDE. So I have this stochastic PDE, okay? So
Yes.
this stochastic PDE is given by this three deterministic term and this stochastic part, okay? Yeah. What I want to use here in order to study the limiting behavior of the solution of this SPDE, what I want is, if you want, to give a probabilistic representation of the solution of my SPDE. My SPDE is already a probabilistic object, okay, because it's a partial differential equation where you have this random term here. So my SPDE is a random object defined on some probability space. But then what I want in order to study the limiting behavior of the solution is to give a probabilistic representation of the solution. What do I mean by this? What I mean by this is that I want to write, let me see if I find this. Yes, here. What I want is to write my equation. I wrote my equation in integral form by using this S epsilon. But this S epsilon is not just a semigroup, but is the semigroup associated to some diffusion, which is the diffusion X epsilon, and is the analysis of the limiting behavior of this diffusion X epsilon that allows me to get the limiting behavior of U epsilon. So it's fundamental that this S epsilon is represented by this form here. Okay, so what I have is that S epsilon is given as the expectation of phi of X epsilon, and the X epsilon is the solution of this SDE. So what I want is to use, again, I repeat, a probabilistic representation of the solution of the SPDE, because I want to prove, I want to prove my result by using the limiting behavior of X epsilon. And X epsilon is what is fundamental here, and this is obtained, as I was saying, you see, by a perturbation of an Hamiltonian system with a small noise. Then you do a time change, and you get this equation here. Okay, and I introduce, you see, the transverse, the slow component of the motion of X epsilon is what I want to study. And by understanding the limiting behavior of the slow component of the motion of X epsilon, I can get the limit for the solution of the SPDE. So here, somehow, I need a semigroup because this is all what this is about.
Yes, yeah, I understand the role, the main role of the semigroup here, but yeah. It means that if we replace the Laplace operator by another operator, that we cannot generate a semigroup. So I just want to ask.
If you replace the Laplacian with a more general operator, this means that you have a more general stochastic perturbation of your Hamiltonian system. So, for example, if instead of taking the Laplacian, you take, you have an operator with coefficients that are not constants, then this means that when you take your perturbation here, instead of having a perturbation just by putting a Brownian motion, you have, I don't know, a perturbation with multiplicative noise, and so in that sense you get a more general second order.
Okay, I see. The semigroup S epsilon here is dependent mainly on the gradient bar of H.
So right? What I want to say is that depending on the type of random perturbation that you take, you see, you can perturb just by adding dW, okay? And this is giving you, and if you do this, this is giving you for the operator L epsilon the Laplacian. But if you perturb by, say, sigma X epsilon dW, then what you will get is a second order operator with a non-constant coefficients.
Okay.
I cannot tell you anything, and I think that this would be, much more complicated. My student has done something about the Friedel-Wenzel limit when here you have a non-constant coefficient. Nothing dramatic happens in the sense that the result is still provable, but it adds huge technical difficulties instead of having additive noise perturbed with multiplicative noise. But still, you can do things, but it's much more. And apart from this type of a perturbation, I don't know any other type of perturbations. I wouldn't.
Okay, thank you.
Okay.
Thanks.
So I would suggest to move discussions to the coffee break meeting, and I would like to thank again Sandra for a really very interesting talk, presenting very interesting problem. And let us finish our meeting, unless there are more questions. Okay.
No more for me.
Okay, so see you in a few minutes, and I will close the meeting. Thank you. Thanks, everyone.
Bye-bye.
Thanks.
Bye.
Thanks.